there's two talks that you're going to see today. You're going to see a talk by first by Megan Gambs, who is a researcher in the oceanography department at here at the University of Washington, and she talks about how the Missoula floods during the coming out of the last ice age, the role that they played in affecting not only the ocean salinity, but also that effect that those floods had on the atmosphere and the climate, and so the longer term impacts. And then I'm gonna have a talk as well, and I'm gonna take you really far back in time, and I'm gonna talk about snowball Earth, which is this idea that during the Neoproterozoic, which is a time period about 600 to 800 million years ago, that the Earth's oceans were completely covered with ice everywhere. And so this is a very exotic kind of idea, but there's some strong evidence for it. We seek to understand not only the changes that are happening right now and that are going to the future that are being forced by changes we're making. So we're putting in carbon dioxide in the atmosphere, and that's having an effect on our climate. But what's actually interesting as well is the internal dynamics of the climate system. So what is the Earth capable of experiencing in its range of climates just on its own without these kind of external forcings? And I think those are interesting questions too. So to be able to understand, and I think you have to be able to understand what what the climate of the future will look like, you really have to understand what the range and the variability of the climate is under the Earth's own internal processes that are just going on. So these two talks are more about these have some forcings which are not anthropogenic in nature, but are processes that caused by long-term geologic processes. So, for example, the Missoula floods were caused by the Earth coming out of the Ice Age. And so as the Earth's coming out of its Ice Age, things are warming up, and liquid water is starting to melt, and it builds up in these big lakes. And it turns out that there was a big lake near modern-day Missoula, Montana, that was dammed at one end by basically a big giant chunk of ice. Okay, so we call it an ice dam. And that ice dam is inherently unstable. It's warming, and it's going to be melting. And eventually that dam fails. And when that dam fails, it releases a tremendous amount of water into what is now eastern Washington. And that's and that water actually carves out a significant portion of the lower Columbia River. And then in my talk, I'm talking about the snowball Earth. So, snowball Earth is probably caused. Well, it's unknown exactly what caused the snowball Earth, but I think that it probably is due to changes in the configuration of the continents, and it also has to do with the fact that our sun at that time was a little dimmer, and so how can we understand the mechanisms of the climate? So I think what Megan's doing is a terrific climate experiment. So what she's kind of doing is seeing, well, what happens if you have, what is essentially the amount of fresh water that is about the size of one of the Great Lakes, like Lake Superior, if that enters into the ocean instantaneously. So the ocean's very salty, okay? And so what that means is that when you add that fresh water to it, you're freshening up a tremendous amount of water in the ocean instantaneously. And the ocean depends on its saltiness in order to mix. So when you freshen up this water, it allows mixing to happen at a kind of an unprecedented rate. But it is fairly restricted. But what she's able to see is that even this single event of the Missoula flood can have a lasting impact for years on the Earth's climate system. And so we've seen other systems like this. There's eruptions of volcanoes, which can actually dramatically impact the Earth's weather on the timescale of years to even decades. and that's just single events. And so, but I think a big question that people have when we talk about climate change is people always ask, well, is this a natural system, or a is this actually an anthropogenic or a human caused thing that we're doing? And so what we do as climate researchers, we're trying to discover and determine what are the natural what are the natural scenarios that are out there. So what could we achieve with climate change, or what could we achieve without these anthropogenic forcings? And then what we do is we see, is what we seeing any different from that? And I think that the answer is yes. So we are seeing climate change that is different from any kind of natural forcings that we can give. Okay, so we can kind of understand what the forcings are from volcanic eruptions. We understand what the forcings are from variations in the sun's intensity. So the sun is slightly less and gets slightly more intense, slightly brighter, and slightly dimmer over about a 10-year time scale, and we understand that phenomena. So, yeah, but I think it's really important to be able to understand what the Earth's the climate system is capable of on its own before we start making predictions about where that climate system is heading under this external influence of adding carbon dioxide to the atmosphere. Yeah.
Before I get started, I just wanted to get all of my acknowledgments out of the way. So I wanted to thank the Engage program for letting me do this, as well as Town Hall and the National Science Foundation, who funds my research, along with both of my advisors, Leanne Thompson and Susan Hadala, who have the grant through the National Science Foundation. I'm in the School of Oceanography at the University of Washington, which is under the umbrella of the College of the Environment, and I'm part of the program on climate change. So today I'm going to talk to you about water, rocks, and the tropics, and try to answer the question, did the Missoula floods impact climate? But before I get started with that, I wanted to give you a little bit of background on how I got here. So as an undergrad, I studied these microorganisms called foraminifera, and they tell you, looking at the oxygen isotopes of these, you can understand when we have had ice ages in the past. And then I went on and decided that I wanted to study volcanology because I thought it was totally cool and kind of exotic. So I spent months and months in the field with a giant sledgehammer, which was incredibly heavy, and was out there during hunting season, which was unpleasant. But I got to look at all these really cool old rocks, and I got to analyze them, and I thought that was really interesting. But I sort of thought, this is millions of years ago, and that's really cool, but what happened to climate when you have these huge volcanic events? So I applied to graduate school, and I'm lucky enough to sort of marry the two, looking at catastrophes, but not just at the catastrophe, but what are the climatic implications of these catastrophes? And so this is me studying oceanography in a Gumby suit on a ship in the middle of the Pacific Ocean. And in the middle of the Pacific Ocean, we picked up this rock, which is a Columbia River basalt. And it reached the middle of the ocean, or the bottom of the ocean, by the Missoula floods that I'm going to tell you about today. So I thought this would be a nice opener. Here's a map of what the Earth looks like today. So you see North America in the center. And all of the white is areas where we have ice sheets or ice. So you can see that there's ice in Antarctica and ice over Greenland and around the North Pole. But 20,000 years ago, we were in an ice age. So that meant that there was a lot more ice on land. So you can see that the ice extent over Antarctica was much greater, and you see way more ice over the northern hemisphere. And if you noticed, the continents seemed to be bigger during the last ice age, and that's because sea level was lower, about 400 feet lower than it is today. So all of our coastlines were much further out than they are today. And that's because all of the water from the oceans was taken up into these huge ice sheets. And these ice sheets were over a mile high. So we're talking a lot of ice. So here is a map of the Pacific Northwest today. You can see the outlines of the states, and Seattle is indicated by the yellow star. And here is that the lowering of sea level and the extent of our coastline expanding during the Ice Age. This is the Cordilleran ice sheet, which is was a minor ice sheet. On the other side of North America, we had the Laurentide ice sheet, which is this huge ice sheet, and it's very popular in scientific research. Climate scientists have found that during the last deglaciation, so when these ice sheets began to melt, water streaming from the Laurentide ice sheet caused dramatic climate change. It caused ocean circulation to slow down, and it caused changes in climate, so a cooling of the atmosphere. But not many people have actually studied the Cordilleran ice sheet, the smaller one on the west coast of North America, but this is what I study. So right here is Glacial Lake Missoula, and Glacial Lake Missoula is the subject of today's talk. And I wanted to sort of explain what Glacial Lake Missoula is in sort of a very schematic way. So imagine a depression, like a valley. So this is looking from above in a map view. And you have water that sort of pools in this depression or valley. And then along comes a lobe of that Cordilleran ice sheet, a glacier essentially, just a big glacier. And so it acts as a dam with this water reservoir building behind it. But then periodically, this ice dam fails in some way. And then all of that water that was built up behind it in this reservoir is able to flow out very quickly. And so here's a view of the actual valley that the reservoir of Glacial Lake Missoula existed in. And that water, half the volume of Lake Michigan, flowed out within an order of hours. Think about that. So this is a giant wall of water filled with icebergs and sediment, and it's just rushing out towards the coastline. So along the way, this very turbulent water is picking up rocks and it's scouring out the landscape. So that's how we get the scablands of eastern Washington, if you're familiar, on your way to Wazoo. Unless you're a Husky and don't want to go there, that's fine too. But this is one of those boulders that has been scoured out, and you can see how huge that is. And this is being carried by this flood. So this is something that is tremendously catastrophic. In fact, there's evidence that the water reached over 1,000 feet high, which is about 2 Space Needles tall. So this is a huge, huge event that's happening very, very quickly. And recent work from the U.S. Geological Survey has shown that the floods emptied out through the Columbia River and into the Pacific Ocean within an order of weeks of that ice dam collapsing. So this is happening when you think about the ocean. This is happening basically immediately. This is a fast, very, very fast event. So there's been a lot of work looking at where these floods flowed, and so the black line sort of shows you where schematically we had these flood events flowing. But there hasn't been a whole lot of work looking at what happens when you all of a sudden dump all of this fresh water into the Pacific Ocean. And that's where our research comes in. And what we ask is, what happens when these floods reach the Pacific Ocean, and how can these floods impact climate? And to do this, we use a climate model, a computer climate model. So this is the same kind of model. It's the same model that's used to understand what the future climate looks like with increasing CO2 into the atmosphere, except we're using this model and setting it up so it simulates what the Earth was like 20,000 years ago. So that's going back to that first photo I'd shown, or the first photo of the Ice Age. The model has kilometers of ice covering all of the continents and lower sea level to simulate that. So this is what the freshening looks like in our model. So Seattle's marked by the black star, and the blue shape is where we have said, this is where the flood happened. So the salinity is decreased, so it appears as if we've dumped this fresh water in to the ocean. But before I go on to talk to you about more ocean stuff, I kind of wanted to orient you because it's often complicated to look at the ocean. So far we've been looking at map views of everything. So that's where I've labeled ocean surface. We've been looking at that view. But now we're going to start looking at what happens at depth. So looking at the side, sort of where the fish live, and looking at the actual ocean. So to do that, we sort of take slices through the ocean, say like along this red line. And in a vertical section, it would look like this. So that red line would be there, and now we're looking at it from the side. Is everybody on board with that? Yeah? Okay. So the brown there indicates where we have the continent. And so the dark blue is the ocean, and then the lighter blue is the atmosphere. And so north is heading away from me on the stage, and the equator is closest to me. Are we still good? You guys respond a lot more, you're more verbose than many introductory oceanography classes. So thank you. Well, that's possible, yeah. So here's the North Pacific, and that's what I was showing you before. So we're kind of near, looking at the side view, we're close to the Pacific Northwest. And then by the equator, that's the tropical Pacific. So in side view, this is where we've imposed the freshwater flood. And this is what it looks like in the model. So in the left corner, you see the picture that I showed you before from the model, and this is looking at a side view. So we freshened the top 1,000 meters of the ocean, and this is sort of an intermediate flood event, we believe. So what we see in the model, and what I've drawn for you to make it a little bit easier to follow, is initially there's mixing, and then that mixing changes ocean temperature, and we find that on the perimeter of where we have freshened the North Pacific, you get warming on one side and cooling on the other side. And that allows heat to transfer from the ocean to the atmosphere. And when you're transferring heat, we energize the atmosphere. And I'm going to stop there for a second and go back and talk to you about the tropical Pacific. So keep this in your mind. We'll come back to it in a minute. But I want to give you some background on the tropical Pacific because it's an incredibly dynamic and fascinating place. And you need this background before we move on to the next part. So this is the tropical Pacific Ocean. This is Central America, South America, Australia, and Papua New Guinea, just to orient you. Here's the equator, 5 degrees north and 5 degrees south. So those are lines of constant latitude. And this red blob here, this is the Western Pacific warm pool. And so this is this warm water mass that remains at about 84 degrees Fahrenheit, or about 29 degrees Celsius, all the time. It's bath water, essentially, in terms of warmth. And so that is able to stay near Papua New Guinea and Australia by these trade winds that blow from the east to the west. But periodically, what happens is these winds weaken, or they reverse direction and head from west to east, which allows this warm pool of water to move towards the eastern portion of the tropical Pacific. And we as scientists like to quantify that, to sort of make measurements about this. So what we do is we look at the ocean surface temperature in this box, which we call the Niño 3.4 region. And we take the average of all of the temperatures that we measure in this area between 5 degrees north and 5 degrees south, and we come up with a single value. So as the picture is shown here, this would be a La Nina event. Are you familiar with El Nino and La Nina? Yeah. So during a La Nina event, you know, you probably wouldn't want to get a season ski pass here, right? So I'm glad you guys are familiar with that. So, and then this would be an El Nino event where you have that warm water in this box. And so here is a map, or here is a graph that shows the value, the average sea surface temperature in that region through time. So you can sort of by eye pick out some big events, some warm times, like the 1982-1983 El Nino event and the 1997-1998 event. I remember that one particularly because I remember being stuck at school until midnight because the entire neighborhood was flooded. And we had to wait for the fire department to come and take us all home. But this is sort of difficult to look at because it's sort of difficult to see where the El Nino events are and where the La Nina events are. So what we end up doing is we look at sort of the unusual years, the differences from the average. And so the red regions on this graph show you when we've had El Nino years, and the blue tell you when we have had La Nina years. So again, here's the 1997, or here's the 1982-83, and then the 1997-1998 El Nino events. Okay, so let's go back to this picture. So the atmosphere has been excited by this transfer of heat from our freshened region, and that allows winds to spin up. So we call those anomalous winds, but they're just unusual. They're different from the norm. And so those winds are very similar to these weakened trade winds or these reverse direction winds. And what we see with these anomalous winds is that we see warm ocean temperatures. And what we're actually seeing is El Nino events that are triggered by Missoula flood events. And this is our version of that graph from the model. And this isn't just one simulation. This is a combination of 7 different runs that we did with the model where we freshened at different times in the different years in the model, and we still see the same response, that you're getting warming in the tropical Pacific within months of flooding the North Pacific with glacial Lake Missoula water. So although Lake Agassiz can change climate dramatically, for long periods of time, we show that glacial Lake Missoula can also change climate. And going back to thinking about El Nino and La Nina, you can remember that snowpack is not so great during La Nina years. And you can see that when you have an El Nino event, this is a map where it shows you every place where climate is impacted by El Nino events. So you see the warm weather in the Pacific Northwest and wet weather in Southern California, and warm and dry conditions in Australia and Papua New Guinea, and that's often when you get those horrible forest fires in Australia. So what I've shown you is that the Missoula floods are, number one, really cool, but number two, that they do have global impacts, which is really interesting. And that's all I have for you.
I'm wondering if it looked to me like after the flood that it got warmer because of La Nina, whichever one, in the Northwest, and would that not do something to the glacier? Was there a positive feedback or negative feedback or something?
You know, that's something that we want to think about and start looking into. Unfortunately, the model we use, the ice sheets are static, so they stay the same no matter what's happening to like precipitation or temperature. But the new generation of models will start to have what we call dynamic ice sheets so that they can change in response to temperature changes or precipitation changes.
Yeah. I guess the bigger question involved in that is like, with climate change, is it self-correcting or does it do the other thing? Is it like, you know, that's what we worry about, right? Like, are we going to do something and then it's going to cause a positive feedback loop and then it's going to go crazy, right? So,
right.
Yeah.
Yeah.
I had a question on your last slide. There was a big lavender circle, it looks like in the northern part of the Gulf of Mexico.
Yes.
And there's no other ovals of that color, and I'm wondering what that is.
You know, I don't know, but I believe. I pulled this from the NOAA website, if you can see from the bottom. But Luann or Susan, those are my advisors who are in the audience. You can correct me if I'm wrong, but I thought during El Nino years we had wet weather also in the Gulf of Mexico region. Is that correct? And it's cold, colder than usual. Yeah.
Okay.
So I'm not sure why it's not the same color as other things that are getting wet and cold.
It stood out.
Yeah.
Thank you.
Thank you very much. Two short ones.
Okay.
Why does freshening the water increase the amount of heat put into the atmosphere? It was freezing water, right? I mean,
It was cold water, right. And in these models, we're not actually, so we haven't set the temperature to being cold. So it's just the ambient temperature of the ocean in the way that we've set up
so
the
it's
model.
the addition of more water that increases the
It's
energy in the atmosphere?
It's the addition of water. We're still looking into exactly why that's happening, but it has to do a lot with the way that we're putting in the fresh water. And just what happens is you're having constant, how should I describe it? It has to do with ocean dynamics in terms of the, when you put in this, when you put in this freshened region, it's not stable. It has to at some point mix with the surrounding water, and that means that density surfaces have to change, and that.
So it may stop circulation or something, and therefore keep more heat in a local area, or?
It's more anomalous heat than yeah.
Yeah. Okay. And how long did this phenomenon persist? Was it more than one season, or how many seasons?
The El Nino event seems to happen.
That was triggered.
It seems to stick around for up to 6 months.
Oh, okay, so every
And now,
time,
but so this is just the initial connection to the tropics through the atmosphere, and we're starting to look at the model on longer term, seeing how this fresh water actually moves in the ocean, and how that eventually, how that affects climate as well.
cool,
Yeah.
thank you.
Thanks.
How big was the volume of water that was released out of Lake Missoula that caused this event?
It was 2,100 kilometers cubed. I don't know what it is in imperial units. It's half the volume of Lake Michigan, or about the volume of Lake Ontario.
2,100 cubic kilometers.
Yes.
Okay. And how often did this occur? Because there were multiple floods.
There were multiple floods. So they believe that initially the floods were more infrequent, but much bigger. So these huge catastrophic events, and then later floods were much smaller. So they think that it could have been hundreds of years between initial floods, but then later floods may have been more frequent, on the order of like 50 or 25 years.
And one more question. What causes the water in the tropical Pacific to always be at a constant temperature? It would seem that there must be a heat source. I'm thinking You said you went into the study of
Oh,
volcanoes.
no, it doesn't.
I'm wondering if it's something, because that's certainly on the Ring of Fire, what causes that?
It's more, well, so the water in that area is all really warm, and so maybe
Yes.
that picture made it look like it's way warmer than surrounding water. It's mostly just that that water is always being heated, and it's just being pushed into place, and it's sort of staying there. It's
I
not
see.
being able to
So it's
move around.
mostly solar heat, solar radiation that's heating it?
Yes.
And then the winds keep it in place? What's the relationship of that warm water to the trade winds? What's causing the trade winds, and why isn't that affecting the trade winds, or do they somehow draw the trade winds to themselves?
So the trade winds are, so that has to do with the way, the fact that the Earth is rotating. So we just have bands of wind
Okay.
that go in certain directions
And that
at
happens
certain
to be where
latitudes.
those bands go, is from east to west? Okay, thank you.
Yeah, thanks for the questions.
So with this very interesting model, then, are you making efforts, or somebody making efforts to look at the geologic record to see if some of these predictions actually happened?
In terms of, so there's some problems with that. So, no. So Glacial Lake Agassiz, which is the one on the East Coast, there are a ton of there's a lot of geologic evidence of what happened in conjunction with that. The chemistry of the Pacific Ocean makes it very difficult for foraminiferas, like what I showed you before, and other what we call paleoclimate proxy records, means of understanding what past climate looked like using like biological things like foraminifera. They can't survive the record doesn't survive in the Pacific very well. We've got some in Cariaco Basin and in Santa Barbara Basin and shallower areas, but we have something called, I won't tell you the time, it has to do with the acidity of the ocean.
But you could, for example, you could look at tree rings in the Southwest.
Right, yeah, I spoke with somebody at Colorado State University, and we haven't followed up, but he was interested in this, and someone
It
else.
seems like a fascinating
Yeah,
thing to do.
and looking at this too, you can see that, other areas are affected, like Southeast Asia, and we have records of monsoons in southern China and in India, and I spoke with somebody from the University of Toronto, and he was interested in looking at that as well. So it is, we haven't done it yet, but there may be things just less traditional than what's been used for Glacial Lake Agassiz. But thank you for the question.
In addition to glacial Lake Missoula, there was also a glacial Lake Bonneville in Utah and southern Idaho. Do we know how those floods from the multiple floods were time correlated, and whether they were ever together to produce a gigantic
Gigantic flood? I don't know the answer to that. I haven't looked at the other floods in much detail, but they were all, during this deglaciation, there was a lot going on. If you have one warm year, this could happen to, I believe it's feasible that would happen, that multiple floods would happen at the same time. And there are even more mega floods. There's evidence of mega floods all throughout Alaska as well, too. So it could be much bigger than just Missoula.
They certainly came at the end of the last glaciation period, so,
Yeah.
okay. Thank you.
Yeah, thank you for that. All right. Thank you.
Hi, thank you all for coming. So I just wanted to start with this pretty iconic image of Earth from outer space. And to me, this image kind of demonstrates a lot. It demonstrates a planet that is full of life, with this diversity of life, over a lot of different landforms. On this image, you can see forests and deserts, you can see oceans and land, and you can see clouds and ice. But it also suggests something else to me. It kind of suggests that Earth is a part of a greater universe, because this is taken from space. And it kind of makes you wonder what else is out there. Well, we've actually been able recently to answer that question a little bit and to see some other planets that are outside of our solar system. So I wanted to just start off by looking at some of these strange planets that we've seen so far. This is an artist's rendition of a planet called Coro 7b. Now, this is a planet that's so close to its sun that at over 4,000 degrees Fahrenheit, when it rains on this planet, it literally rains liquid rock. This is a funny planet. This is called HAT P1, and this is known as the puffiest planet that we've found. And that's because compared to Jupiter, which is the largest planet in our own solar system, it's over twice as wide, yet it contains less than half of the stuff. So you can think of this planet as being like a kind of a giant puffball floating around in space, or kind of like a marshmallow that's floating around a campfire for all of eternity. And this planet is an artist's rendition of Kepler 62f. This planet is the planet that we think is most likely to have life outside of our solar system. It's just the right distance from its sun that it can have vast amounts of liquid water if they're present. Now, here's a strange planet. This is a planet with land and with oceans, but its oceans are actually covered in ice. And that ice is hundreds of feet thick. As a matter of fact, so thick that light can't travel through that ice. And that ice sits atop the liquid oceans. The ice also flows over the surface like big rivers of ice flowing around the globe. So you might look at this planet and you might say, wow, this is a weird planet. And it might seem like it's 600 million miles away, but it's actually 600 million years away, because this is Earth, or this was Earth. This is the snowball Earth, or Earth as it looked like 600 million years ago during a time period that geologists call the Neoproterozoic. This is a time before animals and plants. This is a time before trees and dinosaurs, but it's not a time before life. And so that's what my talk is about today, is how photosynthetic organisms, or photosynthetic algae to be specific, survived the snowball Earth events of the Neoproterozoic. So this is my image of what I think a photosynthetic algae looks like in my brain. I don't use microscopes, so I don't really know. But you might ask, why do I care about algae? Like, they're just, what are they? Well, we still have algae around today, but it turns out algae have done a lot of cool and great things in their career. Algae went on to evolve into plants and evolve into trees, and this evolution actually set up the coevolutionary habitat that allowed for animals like alligators, or the pygmy sloth, or human beings to exist. So, to put it another way, if algae hadn't survived during the snowball Earth, then plants wouldn't be here, and animals wouldn't be here, and you and I would not be here. So, we really need to understand how these organisms survived the snowball Earth, this extremely unique and different time in the Earth's past. So I like to think of this algae as like a superhero, like surviving this extreme event when the Earth was on near apocalypse. So now you might ask a little bit about the snowball Earth. Okay, this is really weird. Okay, so the Earth had oceans, but they're frozen, but they're not completely frozen. Tell me more. Okay, well, first there was the sun. But this was really far in the Earth's past. This is 600 million years ago. And to give you some perspective, the Earth is only about 4.5 billion years old. And so it's actually so old that the sun was a little bit dimmer. So not quite as bright. So things were a little bit colder to begin with. But then the other part of the story comes in is that there's photosynthetic algae. And these algae, they eat carbon dioxide and they produce oxygen. And I have chosen to represent carbon dioxide as this very warm mummy bag, and I've chosen to represent oxygen as just some thin sheets that you might get that wouldn't keep you very warm at night. And the reason I'm using this is because carbon dioxide, when it's in the atmosphere, has the ability to warm a planet. And oxygen doesn't. So if you convert carbon dioxide into oxygen, you're going to cool the planet. And it turns out before the snowball Earth, these algae were really productive and had lots of offspring and actually were able to trigger this kind of event, so causing the Earth's oceans to be completely frozen over. So, okay, so that's really weird. How do we get out of this like crazy snowball that like the Earth's surface is completely covered? Well, the answer, we think, is volcanoes. So one thing that's cool about volcanoes is they don't really care if the Earth's surface is covered in ice. They don't really care if they pop up in the tropics or if they pop up in Alaska. They're just going to do their thing. And so one thing that they do is they erupt. And when they erupt, they emit lava and ash, but they also emit gas. And one of the gases they emit is carbon dioxide. And so over millions of years during the snowball Earth events, the carbon dioxide is allowed to build up into the atmosphere. It doesn't have any place to go. And eventually, the carbon dioxide builds up and builds up that it warms the entire planet, going from a very, very cold planet to an extremely hot planet in just a few thousand years. So that's a weird planet. So where did these things survive during this time? And I'm going to kind of pose to you why that's actually a difficult answer to get to. So algae need two things to survive during this time. They need liquid water, has to be liquid, and they need sunlight. So liquid water plus sunlight gives you the algae. Okay. So if we want to understand how we got from a snowball Earth to a present-day Earth, which is full of life and full of creatures, we have to understand where the photosynthetic algae survived. So, okay, where did they survive? Well, here's an image of snow, and that might be some people's first guess, but during the snowball, it was below freezing everywhere all the time. And so the snow never had a chance to melt into liquid water. So they couldn't survive on snow. This is a picture of a volcanic hotspot that's underneath the ocean, okay? Very warm there. These things would exist during a snowball Earth, and there's liquid water, plenty of it, but there's no sunlight down that deep. So they couldn't survive there either. What about lakes? So lakes have water, right? Yeah, okay. And why couldn't they survive there? Well, because either you're in a place on a snowball where it's snowing all the time, or you're at a place where it's evaporating all the time. And if you're at a place where it's snowing all the time, well, then that lake's just going to be filled in with snow, and you don't have a lake. And if it's evaporating all the time, well, over the really long time periods, the tens of millions of years these snowballs lasted, even the deepest lakes in the world would eventually just completely dry out. So we're going to need a new idea. And so where do the algae survive? I don't think that they survived in Africa, but I wanted to point out one thing here. I wanted to point out the Red Sea, which sits between Africa and the Middle East. And what I want to point out to you is that at its southern edge, the Red Sea is connected to the ocean, but it's also a very long and narrow channel that has land on either side of it. And so I'm going to kind of explain to you, and I call this kind of feature an inland sea. And we expect to see not necessarily the Red Sea during a snowball Earth, but we expect to see features like a Red Sea because of the geologic processes that formed the Red Sea. So why do I think that an inland sea or a narrow channel is a good place for these photosynthetic organisms to survive? Well, I'm going to try to convince you that over the next couple slides. So this is an image of what the continents might have looked like during snowball Earth. So you can see a couple different things here. You can see that you've got land, and you also have ice over the oceans. And so, like our present-day Earth, the tropics, or the equator, is much warmer than the poles. But for a snowball Earth, the tropics might be minus 30 degrees Celsius, and the poles are much, 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 much colder. And so, because it's warmer at the tropics and colder at the poles, that creates a hydrologic cycle, a certain hydrologic cycle. So at the equator, you have what's called sublimation. So sublimation is the process by which ice, solid ice that's covering the ocean, is converted directly into vapor, into gas. So if you've ever seen dry ice, you've seen sublimation. So you've seen that little block of dry ice it doesn't melt, it doesn't go liquid, it just turns into gas. That's sublimation process. And that's what happened to the ice at the equator during a snowball Earth. But that sublimated water will transport to the poles where it is deposited as ice. So what that means is that because it's colder and there's snow falling at the poles, the ice is really thick there. And because it's warmer and the ice is sublimating at the tropics or near the equator, the ice is relatively thin there. It's still too thick to allow light to get through, but it's relatively thin. So because you have that slope or that transition from thick ice to thinner ice, it actually causes the ice to deform and flow under its own weight. And that creates rivers of ice that flow from the poles to the equator. And so I could kind of draw on, we don't really know where these things might have been, but I could kind of draw on places near the equator or near the tropics where inland seas or these narrow channels might have existed. So why do I think inland seas or narrow channels are a good place for these things for algae to survive? Well, I'm going to show you a series of images, and kind of like Megan, I'm going to kind of run you through on the top is going to be a side view, and on the bottom is a top-down view of the same thing. So on the top, we can see ice that's floating on water, and below that, we can see ground. And so imagine you have an algae living down there during a snowball Earth. Well, what's going to happen is that light from the sun is going to try to make its way through this ice, but the ice will end up absorbing the light, and so not enough light will get down there for this photosynthetic for this algae to survive. So algae can't survive underneath the ice during a snowball Earth. So if we're near the equator, then we're in an area where you have net sublimation. So the solid ice that's on the surface is being converted or going away into the atmosphere. It's turning into gas. But you also have these rivers of ice that are causing the ice to flow. So what happens when a river of ice encounters this kind of narrow channel? It goes into this narrow channel. Well, it slows down. And you can kind of think of this as, driving on I-5, and then all of a sudden there's like a big wreck, and then you're down to one lane of traffic all of a sudden. Things get slow when you get compressed. And so this ice that's flowing through here will slow down as a result of that. But at the same time, as it's slowing down, it's also being sublimated away. So it's just go to the atmosphere. So if that channel, that narrow channel, is long enough, then eventually there just won't be any ice left. So if you were on this slow freeway and there were only places to get off the freeway but not to get on, then eventually you're going to reach a point in the freeway where there's just no more cars anymore. So it's kind of like that. And so in this place where the ice that's covering the ocean can't reach, that is a location where these photosynthetic organisms could survive during these snowball Earth events. So here's an image of what the Red Sea looks like. And again, this isn't the Red Sea didn't exist during the snowball Earth events, but we think that places like it may have existed because the geologic processes that formed the Red Sea were also present during the snowball Earth events. And so if you do a calculation, which is my research, to calculate how far ice coming from the southern end into the Red Sea would actually travel into that sea, given the climate that we know, like how fast the ice is flowing and how fast the ice is sublimating away, how fast it's being removed, then what we find is that under certain conditions, it allows for a little pocket of water to remain that the ice that's covering the ocean doesn't get to. And so that's a place where these photosynthetic organisms could have survived and lived throughout the entire snowball Earth events. So, again, if we want to look at Earth today and understand and appreciate the diversity of life around us and appreciate our own existence, we really have to thank these algae for surviving during the snowball Earth event, because life as we know it wouldn't exist today if it weren't for these photosynthetic organisms. So I kind of want to end with a picture of Earth from space, the one I started off with, because I think that if you were on another planet and you were looking at Earth right now with all of its different life and all of its diversity, you would say, hey, there's a planet that has life on it for sure. But if you were to look at Earth 600 million years ago during the snowball Earth, you would probably say that it was a dead planet. So consider that when we're looking out at the stars and we look at some of these strange planets, that there might actually be life surviving, the seeds of life surviving and getting by in these nooks and crannies and these little tiny spots just waiting to flourish when the climate changes. All right, thank you very much. I'll take your questions.
Okay, I got two questions. Nobody's behind me. Could you explain why the ice would sublimate rather than turn into liquid? Was it just too cold for the liquid and some of it would just turn to gas?
Yeah, so the idea is that the surface temperatures are never warm enough to actually melt it, but sublimation happens because there's just wind and things that will cause the ice to go into the atmosphere. So you have to get above freezing to have melting, but you don't have to get above freezing to have sublimation.
Okay, so since life existed on Earth for several billion years before snowball Earth, were there other snowball Earths?
So that's a great question. So during the Neoproterozoic, the time that I was talking about, like 600 million years ago, we think there were at least 2 snowball Earth events. There's evidence for maybe 2 more other than that during that same time period. Plus, there's evidence for another snowball Earth that happened way back in Earth's past, like a couple billion years ago, but that was before these kind of organisms existed at all. So, yeah. So it's happened a few times, it looks like.
Thanks. Well, if nobody else is asking a question. Hey, so 600 million years ago, there was animal life, right?
No. They think there might have been sponges. So
did they survive?
Yeah, they would have. And so, yeah, there's those kind of, so the photosynthetic organisms are really what went on to make, this is before plants, before animals. There's some evidence for sponges, but I think that as far as it goes, that algae are really the most complicated life forms that existed during this time.
Okay.
This snowball Earth was shortly before the Cambrian explosion,
Yeah.
where there's a huge speciation and the evolution of lots of diverse life. The first one, as I understand it, is 2.2 billion years ago. And from what I've read, shortly thereafter, cells with internal nuclei evolved. What is it about the limitations of life that causes huge speciation and quick evolution afterwards?
Yeah, that's a really good question that I am completely unequipped to answer, given my background. So my background is actually in glaciology, so studying how ice flows. So you can see why snowball Earth might be a novel problem to me. But when it comes to evolutionary biology, I have a very fundamental understanding of it, but not super technical. So, I mean, but as far as I know, these are questions that people are still trying to answer. Like, why do we have this great diversity after these near catastrophes? And I think it's really unresolved as far as I know. So. Thanks. Oh, okay. Last question.
Well, that's good because that was my last question.
All right.
You said it ended in 1,000 years. That didn't make any sense to me. When you have volcanoes, wouldn't they have to build up over
Yeah.
a long, long period of time?
Yeah, I must have misspoken. I meant to say tens of millions of years.
Okay.
Yeah, so I'm sorry, you know.
And perhaps I misheard. I'm a little deaf. There are organisms that live in snow. Aren't there a bunch of other places for life to survive rather than in liquid water?
Yeah, so animals presently do survive in snow, but it's snow that does eventually get above melting occasionally. And during the snowball Earth, we don't think that ever
And there
happened.
are no photosynthesizers that exist in snow?
There are, but it's places where it occasionally gets above melting and you can have liquid water. So, yeah, it's a particular kind of photosynthetic algae. And so, if I can get a little more deeper into the problem, the idea of the snowball Earth is not like scientists are still debating whether or not it happened. And biologists are actually people who are saying snowball Earth couldn't have happened because there's no environment for which them to have survived. So the onus is on geologists like myself to kind of try and find these environments where they could have survived.
I see. Are you imagining that these are blue-green algae or something?
Yeah, so there's different, blue-green algae is the specific kind, yeah.
Thank you.
Yep. All right, thank you very much.